okay, it's curly. It doesn't look bad. Okay, we are now live. I'll put it in the chat.
So you're gonna stay up here and then put it down?
Probably, yeah. Otherwise, I can stay up here and manage the slides.
I'm probably gonna sit here after I do the intro.
Okay.
Because I'll just be managing the slides, so.
I can sit there.
Yeah.
Should I sit now?
Sure. Or you can put your computer.
Okay.
Welcome to C 2026. C stands for the Simulation Exploration Experience. So this is 2026, so we've been doing this for at least 15 years here. We used to have in-person events back before COVID times, and this is actually our first time bringing this back in person. So really excited to have you guys here to see this. This is not your traditional conference presentation. This is going to be more of a showcase, so I can't take credit for most of the work. That's going to be our amazing students here in person and online. So C is a distributed simulation student co-opetition, as we like to call it. So the essence of a collaboration and a competition. So we have student teams from across the world. We have teams from even UCF here. We also have teams online that are from London, that are from Brazil. So we have teams all over the world that are collaborating across time zones, across language barriers to make this happen. So this is a really impressive and amazing feat. So I want to introduce you to a few other people I have here. So I am the technical chair. My name is Paige Whittington. So that basically means that I am teaching the students. I'm helping them to learn distributed simulation. What does that even mean? How to use simulations and how to apply them to lunar scenarios. So you can see here we have a picture of the lunar South Pole. We give the teams a scenario each year. So this year the scenario is about 15 years in the future. We're looking at sustained lunar presence. What does that mean to you? So it's kind of open-ended. We've had really creative ideas in the past, such as lunar cable cars, or I think a tomato launcher from the moon. So we really encourage students to be interpretive, creative. We have really great engineering analysis that comes out of this. So I technical chair, I would also like to introduce you to Katie Tuber. She works with me at NASA Johnson Space Center. Katie, would you like to introduce?
So my name is Katie Tuber. I work with Paige at Johnson Space Center on computer simulation and graphics. So I just wanted to say a little words about simulation before we kick off the rest of the events for today. So at NASA, in order to achieve our goals of creating a sustained presence on the moon and beyond, we need to find the best ways to prepare for many different scenarios. We need to be able to train the astronauts and flight controllers who are planning and executing the missions alongside them. We need to be able to make informed decisions about lunar locations, dates, times, and what objectives we want to achieve. Simulation provides us with the ability to train and analyze mission scenarios with very low risk. Flying a vehicle to test how different trajectories, vehicle configurations, and forces which change the way a pilot will fly without any risk or injury to them. It allows us to test out different rover models, hand controllers, and wheels in different configurations before building and prototyping, which will save you time and money. Testing your lunar base and systems health before you build can give you a chance to find any gaps in your planning. And you can test your software with any vendor hardware to make sure that it's working and communicating with the systems how you might expect. So a lot of industries use simulation besides aerospace, and we also do a lot of distributed simulations, which the students have been working diligently on for the past semester. These can go from anywhere from medicine, the automotive business, to Disney theme parks, construction. So any interest that you have could be added, or you could simulate and have a plan forward. So hopefully the students from this semester, we're really happy for all of your work that you've done this year, and we hope that you can take these experiences forward, not just for aerospace industry, but any industry that would allow you to help with analysis and planning for the future. I'm gonna hand things back to Paige.
All right, before we get started, I would also like to introduce Mike Conroy. He's our architecture chair for C in the back there. He is also the senior design professor here at UCF, so he's helped with these students a lot. So Mike, do you want to say a few words before we get started?
Welcome. It's fantastic to be able to do this in person again. Welcome, everybody. It's fantastic to be able to do this in person again. It's been quite a while since we've been able to get the people together. I think it's fantastic you're here. I think it's fantastic we're pulling it all together. And I want to emphasize too, that we talked about the students and what they're doing. Paige knows this. They did a great deal of this without the help they usually get this year. So what you're seeing is fantastic work that was done by students in the capstone senior design process at several universities around here and several universities around the world. And I think they knocked it out of the park. So understand that this is the tools, the texts, and the types of things that NASA uses for their time machine to go look into the future, to go plan the types of things that we're going to do. And the work Katie and Paige, or Paige and Katie, did has been absolutely fantastic as well too. I think they should take over.
All right, thanks, Mike. All right, we have some other people here as well, but we'll get to them when we get to their presentations. So I want to kick things off. So I said distributed simulation earlier, so before we get started, I want to do a quick recap of what that means. So traditionally, simulations are independent simulations. You might build one of a rover or a power system that are completely separate. So distributed simulations can be separate simulations that talk to each other, so they operate in a single environment. This is a very advanced technology, although it's been used for decades. For example, the Department of Defense, NASA uses this as well. Me and Katie work on stuff at NASA. So this is a very advanced technology, and we're excited to be teaching it to university students. I think this is a great path to careers. This is a great moment for them to learn this. It's very advanced technology, and we're really proud of what they've been able to accomplish. So each team has their own simulation that talks to each other. So that is how it works in the distributed simulation framework. So before we get started, I'm going to say a quick thank you to all of our sponsors. We work with a lot of different companies that are able to make this possible. For example, Pinch Technologies, now OneR, gives us our RTI, our runtime infrastructure that allows the students to talk to each other. We've used AWS this year, so we have a lot of amazing people that make this possible behind the scenes. I also want to let everyone know that this is being recorded and live streamed on YouTube. The video feed only shows the front of the room, but I just want to make sure everyone's aware that this is being recorded.
There's also, for you guys' use, there's like stickers and things up at the front you guys can have later. Just don't feel afraid to take anything. And if you guys need any refreshments or anything, there is a room down the hall this way, which has drinks and snacks if you guys need anything.
All right, with that, we're gonna get started with the student presentations first. So each student has spent the semester designing and building simulations. So each one of them has had a chance to give a presentation here today. So we're gonna get started with Brunel University in London, if you would like to take over.
Good afternoon, Paige. Can you hear and see me?
Yes, I can hear you.
Okay. I'm gonna go ahead and get started. All right. Hi, everyone. My name is Radine Shuatreya, and I'll be presenting on behalf of the Brunel University team today. It has been a very exciting season for us in this year's C event, and I can't wait to tell you all about it. But first, an introduction is in order. Next slide.
Can you record?
So we are the Modeling and Simulation Group in the Department of Computer Science at Brunel University. Our incredible faculty team is led by Professor Simon Taylor, who is the Vice Dean Research of our college, and he also is the Executive Chair of the C program. We also have Dr. Anastasia Anagnasto, Dr. Noura Abubakar, and Dr. Mazir Gorbani on board. They've been overseeing the direction of our student team projects in C for many years now. This year, the student team comprised of me as the team lead. I coordinated our meetings with partner teams and developed our federates. Mazir and Tracy took point on the 3D visualization effort, which involved creating the 3D models and setting them up in the NASA Distributed Observer Network. And finally, we have Hao Chuan, who investigated some of the info that's used in our simulation. Next slide. So I'm sure you've all heard about the recent success of the Artemis II mission. It's one chapter out of many being written about our historic return to the moon. A mission of such ambition requires all kinds of supporting infrastructure. Our team's interest centers on supporting the launch and landing capabilities of spacecraft on the lunar surface, which will become very important in later stages of Artemis. Next slide. So since C 2024, we've been implementing the idea of a lunar spaceport that originated in a paper by the RSNH group and NASA, and you're seeing what that looks like on screen. The purpose of a lunar spaceport is not that different from what's already here on Earth, and that is to provide rockets with the services they need to launch safely, quickly, and in a repeatable fashion. This year, our team decided to experiment with a modular architecture that allows a spaceport to be commissioned virtually anywhere that's mission critical on the lunar surface. Next slide. And this is what it looks like. It's an all-in-one platform that's easily deployable onto the surface by a lander as payload. It comes fully equipped with robotic arms for transferring cargo and refueling landers that it hosts. Next slide. So as part of our partnership with Facens University of Brazil and the University of Central Florida, our spaceport is fully capable of interacting directly with their systems. And you're going to see what that looks like later in the Federation execution. Next slide. Now, 14 members across the North and South Atlantic were involved in this three-way collaboration. Through our Discord server, we had dedicated spaces where we coordinated development through regular back and forth discussions, and this resulted in some fantastic output. Next slide. We captured our requirements and those of our partners to create the Modeling and Simulation Group Federation Object Model as shown on screen, or the MSG FOM, and it was created in the Pitch Visual OMT software as an extension to the Space FOM. This formalized the data exchange between the federates developed by us and our partners. Next slide. Now, let's talk about the C HLA Starter Kit. This is a Java software library that was conceived by Alfredo Garo and his brilliant team at the University of Calabria to reduce the complexity of creating HLA federates in C, and it's empowered student teams in C for well over a decade. But since its original release, the Java ecosystem has improved dramatically, and HLA4 has arrived on the scene. Next slide. And so, Building on this legacy, I collaborated with Pitch Technologies, who are now BAE Systems 1ARC, for my senior undergraduate project to develop a new version of the starter kit that brings the latest and greatest advancements from the Java ecosystem, HLA4, and even easier ways to create veterans for student teams. Next slide. Now at Brunel, we've got a lot of scar tissue from our previous experience working with the HLA and Space Bomb. We had to work with a lot of trial and error to get our configuration and systems right. And so this inspired me to create the C baseplate, which is a starter project template that accompanies the framework, and it's bootstrapped with everything student teams need to get up and running, with the same kind of build pipelines that are used by industry professionals. Most of the simulations you'll see today are powered by this new version of the starter kit. And our users have actually told us some really great things about their experience working with it. Next slide. Jose Lewis, one of the main developers on the Fastens team and first-time C participant, found the learning curve to be quite gentle, and the entire setup process was way less daunting than it could have been. Next slide. Evan Graff from the UCF base team said that the abstractions that were provided by the starter kit made the HLA integration very simple. The framework liaises with the HLA API, and you only had to work on the simulation logic and declaratively define the data models. At Brunel, we couldn't be happier to build tools that makes modeling and simulation more accessible to users all around the world. Next slide. This has been our best year yet, and it couldn't have been possible without all the overwhelming support we've had. I want to thank the modeling and simulation group faculty for their research support, my fellow team members, and our international partners for all of their efforts. A huge thank you to Paige, Katie, Zach, and Mike Conroy for enthusiastically organizing the C event and tech tag-ups year after year. I would also like to thank 1ARC for providing us with world-class tools and support that enabled the development of the new CHLA starter kit, and of course, the original author team from the University of Calabria. We can't wait to show you something even better when we meet again in May 2027. Thank you.
All right, thank you. Next, we're going to have Embry-Riddle University, and I want to first take a quick thank you and hello. We also have in our audience Carl Siebel, who's traveling here from Embry-Riddle worldwide. So thank you very much for being here with us, Carl.
Thank you. Hello, everyone. My team, can you hear me?
Yes.
Cool. My team and I are representing the Embry-Riddle Aeronautical University Worldwide campus, participating in this event as our capstone design project for our Bachelor's of Science in Engineering. Next slide, please. There are 15 members on our team, split into 5 groups. The power sub-team consisting of Cynthia, Jason, and Jacob. The life support sub-team being Eric, Danielle, and Daniela. The communication sub-team consisting of Tran, Ed, and Jeffrey. The code and simulation team being Ryan and Glenn. And the CAD team consisting of Joshua, Emily, and Josephine. Our advisor for this project was Dr. Carl Siebel. Next slide, please. Pictured here is our baseball card for the Autonomous Resilient Cislunar Habitat, or ARCH. The overall design for this habitat is a structure that takes concepts of previous successful missions in space to create a safe, functional, living, and working space for teams on the moon. The main power source is a molten salt and metal reactor, with solar panels being used to charge and maintain the regenerative fuel cells used as primary power storage for the habitat. The capacity of these cells being represented as battery charge in our simulation. The major life support characteristics of the habitat are temperature, oxygen, and carbon dioxide regulation, each making use of legacy hardware to monitor and control their respective values through the active thermal control system, oxygen generation system, and the sorbent-based atmospheric revitalization system. Next slide, please. This slide shows a simple rendering of our habitat consisting of 5 domes. The central dome is designated for communal living, the others being used for hygiene, utilities, crew quarters, and the airlock system. Together, these compartments provide a total internal volume of approximately 176 cubic meters. Next slide, please. Our project simulates 3 tightly coupled subsystems of a sealed lunar habitat and is designed for numerical integration, where state derivatives are computed at each time step and used to advance state variables. The first simulated subsystem is the thermal subsystem, which models the habitat's temperature dynamics under lunar conditions. The second is the power subsystem, which tracks solar power generation and battery state of charge. And the last simulated subsystem is the life support subsystem, which models crew respiration, CO2 removal, and oxygen generation in a closed volume. The state variables for temperature, charge, and oxygen quantity and carbon dioxide quantity are each integrated using the respective derivatives and the control flags for heater power, CO2 remover operation, and time of day drive the system behavior. Next slide, please. Alongside the TRIC software model, we also developed a physical thermal validation experiment to test the accuracy of our simulation results, which gave temperature data points for heat transfer through a vacuum, verifying our simulation's accuracy to within 5%. Next slide, please. Some of the lessons our team learned throughout the course of our project include the importance of redundancy and reliability in the lunar environment, and the importance of development with future expansion in mind, as well as determining a suitable location to ensure mission feasibility, being the South Pole, and the importance of collaboration to develop stronger ideas. On behalf of our team, I'd like to thank Dr. Siebold for his guidance throughout these past 16 weeks and for making this project possible. Thank you.
All right, thank you very much. Next will be Fassins from Brazil.
Hi everyone, I'm Luisa and this is Jose, and we are representing the Fassins team. Next slide please. So our team is composed by the professors Fabrício Torquato and Thalita Berbel, the development team Kaique, José, Pedro Salviano, Pedro Dias, and Agatha Duarte, myself, for the technical writing team, Luis, Auro, Julia, and our 3D modeler, Mayara Lima. Next slide, please. So in this year, we made a cargo rover that is designed to move across lunar terrain, carrying tools, supplies, and samples to a designated area. The data elements are position, battery level, velocity, and condition status. The tools used were Blender and Substance for the 3D modeling, and Java for the programming. Next slide, please. To choose the location of the rover, we did something different this year, and we made a Python script that scans the terrain to find the flattest, most rover-friendly area. So it works by analyzing factors like slope, roughness, and height variation. And by doing that, it lists the best areas. So you can see in the map that it has some pink dots, and these pink dots are the best areas for the rover. So we choose the dot 3, a spot nearby this dot. And next slide. Now, this is one of the core parts of our project, the rover AI dispatcher. It is responsible for deciding what the next action of the rover will be. For example, continue the mission, accept a new one, go recharge, or wait. To do this, the system analyzes multiple factors, such as the rover's battery level, the current state, the distance to the charging stations, and the available missions. All this data is organized into a decision context and sent to the AI. But to do this safely, we implemented a validation system. And if anything goes wrong, it goes to the fallback policy. That is, continue the current mission, select the best available one, recharge if needed, or wait. So overall, the dispatcher allows the rover to behave in a more adaptive, intelligent, and robust way, while still maintaining full control and safety. For example, if the rover has low battery but is doing a mission in the same time, it can decide whether to finish the mission or to go recharge first. Next slide. So during the project, we faced a few challenges, and the first one is that the team was renovated, so only Kaique and Julia participated in the other years, and most of the team have to learn everything from scratch. The second point is that it was hard to schedule meetings that everyone from the teams that we are collaborating could participate as well. And the third challenge was that our university's main network blocks the connection with pitch. So for example, right now we're doing this with 4G. So yeah, that's it. Next slide. We also learned a lot of things, and the three principal ones are that we improved our logical programming, and we got a better understanding of the DOM framework, and we also improved in the documentation practice throughout the project. Next slide. So here we have our final 3D model, and to do that we analyzed previous rovers that NASA did, and we realized that some features are mandatory, and we also tracked a few optional features, and we were able to apply all of the mandatory features and the optional features that are listed in this slide. And that's it. Thank you everyone for this. Thanks.
All right, thank you very much. Next we have Florida Poly, who are here with us today in the room.
Testing, 1, 2, 3. Hello, we are Florida Polytechnic University Team A, and we are a passive. Next slide. So our team consists of 7 total students. Those present are myself, Alexander Polter, to the left of me, Anthony Fiorio, and to the right, Nicholas Stretch. Next slide. So since we lack the computer science background to complete many of the active team milestones for the SE 2026 round, we worked with Mike Conroy and Paige Whittington to reformulate our problem statement such that it allows for analytical prototypes and mission architecture with a focus on subsystems for the lunar base. And these are some of our project goals. We focus on addressing the extreme lunar environment. Next slide. So we've broken our project into 4 subsystems, those being the base design, seismic isolation, the anchoring mechanism, and the reflector array. Next slide. So moonquakes. Moonquakes happen on the moon at least every 14 days. So to protect against these, what we've done is we've devised a sliding bearing base isolation system, which effectively decouples the ground motion from the base motion. To model the complex behavior, the nonlinear behavior of the sliding bearings, we have opted for what's called the Bauquin hysteretic mathematical model. To test our model and consequently to test the base isolation design, what we've done is we have subjected the model to a moonquake 10 times as strong as the strongest recorded during the Apollo 17 mission. And doing so, we get the numerical results seen in the bottom right graph. And we have achieved a reduction in the seismic effects of 40 to 100 times with this model. Next slide.
So for the base design subsystem, we have the radiation shielding component. This was mainly put in place to protect the astronauts that would be habitating the bunker from the harsher environment radiation. We have found that lunar regolith serves as a good shield that is also found in the lunar environment to reduce costs like from shipping to Earth to protect against radiation. We have found that a 3-meter layer of lunar regolith on the outside of the dome would both prevent structural loading from like overcoming what we had as support and also protect the astronauts correctly. We also have a 30 centimeter layer of polyethylene liner underneath that, which serves as additional protection for the astronauts. Next slide. So on the base geometry component for the base design subsystem, this is underneath the polyethylene liner. We have a sulfur regolith concrete layer, mainly meant to protect against micrometeorites and also to support the base's structure. Underneath that, we have an aluminum 7075 ripping dome that is meant to support the concrete structure and all the weight of the base from collapsing inwards on top. You can see there's a little bit of a remodel there on the top right. And the sulfur concrete can be made from in-situ resources entirely, and the aluminum 7075 dome would be shipped in. And on the anchoring mechanism subsystem, we have these auger-style anchors that would be put underneath the sliding bearings for moonquake mitigation. These are modular, so you can extend them as much as necessary into the lunar regolith, and they basically just drill in to keep it held in place, so it doesn't shift from side to side. And these would also be shipped from Earth, but they aren't the most suitable part of the subsystem.
Next one.
And so one of the other problems we wanted to address is shadowed regions. So on the lunar south pole, there's plenty of craters that are permanently shadowed and sunlight doesn't reach them. For this reason, there's a lot of ice there, and they're also good sites for telescopes. And so one of the ways we want to address getting power there is by having a bunch of solar panels in a bright region, and then you use a laser to transport it to the ridge of the crater, and then reflect it down into the crater where it could be received using a thermal sink or more solar panels. And we proved that this was feasible with about 20 kilometers of travel distance, because there's no atmosphere on the moon, its absorption is negligible. And the constraints that we considered for that were beam diffraction and angular alignment concerns. And this is about 16% as efficient as just generating the electricity directly. Next slide, please. And so here's a diagram of all four subsystems together. On the left is the base design with the ring dome and the radiation shielding. Below it is the moonquake mitigation system using the sliding bearings, and anchoring that to the moon's surface is the modular auger system, and then on the right is the previous subsystem for exploration. Next slide, please. And so some of the main takeaways here were that we achieved designing a few subsystems to make life on the moon easier and also exploration. And we also just pieced those together in a nice way. And some of the future goals are to analyze how temperature swings would affect these systems and also simulate it directly. And we also want to address concerns with lunar regolith because the material properties are not very well known. And some of the skills that we developed were working with Ultera software to gauge how much radiation exposure a human would have with these systems. And also we just developed our 3D modeling skills better. And that's it.
Thank you very much, sir. It's great to have you guys. All right. Next, we have IMT Minds from France.
Yes, hello everyone, can you hear me, Paige?
Yes.
Right, hello everyone, so we are the IMT Minales team. Before we begin, thank you for everyone for supervising this project. So can you go please to the next slide? So we are split into two teams of 7 students. So in the HLA development team, we had Matteo, Carico, Pauline, Menu Pergola, Vanessa Chambon, Yunus Salem. For the modeling team, we had Matthias Almond-Ping, Taha Hablouj, Youssef Hayani, and the supervision team consists of Aubrey De Paul and myself, Leonard Bau, and Gregory Zakharevich. Can you go please to the next slide? So the first system that we developed is the waste storage system, which basically consists of stocking all of the waste or basically elements that are broken or need repair in a storage system across the base, so that basically waste doesn't add up with nowhere to stock it. Can you go to the next slide, please? The second system that we have developed is the waste dismantling system, and it's the one that acts as an entryway for all of the waste that will arrive to our federations. And it basically acts as a gateway between all of the waste that's coming in and the other two federates, which I'll talk about next. It scans whatever is coming in and decides if it needs repairs or if it's beyond repair and needs to be dismantled to be stocked for further use. Can you go to the next slide, please? So this is the third system, and it's the second of the systems that interact with the dismantling system. So this is the transformation system, and it basically repairs anything that comes its way to be able to basically be reused, or if we need any fabrication done, it is also the system that does it, based on whatever we have in stock. Can you go to the next slide, please? And this is how we split our interactions. So the dismantling system basically sends anything, all the materials and all of the information that comes into the transformation system based on its status, as I just explained, or to the storage system after dismantling, and if it requires some kind of storage, and vice versa if we need to dismantle any items. For the waste transformation system, or the WATS in this case, it's going to as I said, send repaired waste to the storage system or fabricate some required parts or elements, and the rest is redundant since it goes both ways. Can you go to the next slide, please? And this is how our 3D models look. So you can kind of see in this slide where the WASS or WAS is the one with the conveyor belts. That's the WAS, sorry. That's a dismantling system, so that's where the waste will come in, and then based on the scanning, it will either go to the WATS, which is the green building, to undergo repair, or it will go directly to the storage system to basically be stocked afterwards or shipped out, depending on what is needed as an interaction. Can you go to the next slide, please? Some of the challenges that the team faced is that this is their first experience working on a large-scale international project, and it was their first experience in this specific project since everyone from before graduated, so it's a new team. It's also their first experience in distributed simulation and HLA standards, as well as a lot of new software to discover and manipulate in terms of modeling and pitch, for example. Can you go to the next slide, please? Now, for the lessons learned, well, one, they gained a lot of knowledge in space exploration and related knowledge. They acquired new skills in CAD software and additional programming skills in Java. They also learned about HLA and how to implement certain scripts based on the standard, and given that they are across different years, they came to learn how to efficiently work together. Can you go to the next slide, please? And basically that's it from us for this presentation. Thank you for your attention, and see you on the next one.
All right, thank you very much.
have the Little Catholic University. And we actually have a few members of the university here as well in the audience, so thank you guys for being here. And I'm gonna hand it off to Lil.
Everyone listen to me?
Yes, I can hear you.
Okay. Hello everyone, my name is Isema, and I am a student at École du Numérique at Lille Catholic University. Today we are going to present our work for this year's C events. Can you again, please? Yeah. This year, our project went from 1 federal to 5 federal. We will introduce them step by step. Each federal has a different role, and they work together as part one lunar missions. Our teams have met several students. Can you the next again? Okay, this is our teams. It is made of several students from our faculty, and each person works on a different part of the project. Next, please. For the first rover, For the first rover, let's talk about HRV, Emergency Response Vehicle, which means this is the first federal we created last year, and this year improved it to work with the new federate. The mission of HRV is to help damaged machines or people in dangerous situation on lunar area, because during the real lunar mission, problem can happen at any time. And the federate will serve emergency signal with coordinates. Can you? Next slide, please. Again. So, the federate will serve emergency signal with coordinate and information about the damaged machine. Then it goes to the location, check the condition and the machine, and safely bring it back out to the base. After the mission, the vehicle will turn to standby mode, and we shall be waiting for another mission emergency. Next is our second federate is LSPF, so Lunar Solar Power Station. This federate gives electrical power to the lunar robots. Can you next slide, please? So LSPS gives electrical power to the lunar robot and machine to a solar charging network. The system always checks the energy need of the different station. Fixed stations send these energy requests, and the federate send the necessary energy to them. Next slide, please. Also, when a robot has a low battery, it sends a signal with its position. The federate then finds the closest charging station and gives the robot there to recharge. Next slide, please. Next one, we have GTPL, the weather and track printer rover. The mission of this federate is to build lunar road and launching area using lunar regolith, which is lunar dust and soil. The rover processes the lunar dust and makes the regolith using microwave heating technology before creating a solid track behind it. This helps create a stable road for transportation. Can you?
again. No. Please. Yeah. Thank you. No, this help create stable routes for transportation and several landing area for future missions. However, this process needs a lot of energy and depend a lot on logistics and material. So the rover need the support of the other system to continue working correctly. So now I will give the rest of the presentation to my colleague Mark. We work more closely with the other system.
Okay, next, thank you, Isema. And next slide, please. So continuing our federal is THRM, which stands for Thermal Control and Radiator Farm. Next slide, please. THRM is responsible for maintaining the safe temperature for all lunar systems, which is extremely important because the temperature on the moon can become very extreme. The system collects the thermal data for all connected assets, which then estimate the cooling capacity available and distribute cooling resources depending on system priorities. The cooling process uses circulating fluid that transports from all the machine to the radiator before the heat is dissipated into the space. The THRM also provides cooling recommendation. It can reduce the activity of system and prevent overheating, and it can also generate alerts depending on the temperature conditions. Next slide, please. Now we will proceed to our final federal, LDMR, the Lunar Dust Mitigation Rover, or as we like to call it, our Lunar Roomba. Next slide, please. Lunar dust can become a major problem because it damages machine and critical infrastructure over time. The road can become a major problem because it damages machine and critical infrastructure over time. So the role of LDMR is to clean the regolith from the facilities. LDMR works with sensors placed around the facility, and when dust reaches a certain threshold, the sensors send a signal with the coordinate of the area that needs cleaning. LDMR then moves to the location, check the environment, and start removing the printer rubber and start removing the dust. Next slide, please. Some of this dust is dispersed while some is collected and reused as material for the track printer rubber, which is GTPR. After finishing the task, LDMR returns to the standby mode and recharges. So it uses the LSPS, and it can also use the THRM if there is a problem with heating, and we can also use ERRV if there is a malfunction for this rover. Next slide, please. Now regarding our challenges, we faced most of them next slide, please. Most of our challenges came from the fact that we decided to implement 5 federations this year, which was honestly a bit ambitious and led to a lot of logistical issues. One of the biggest challenges was federate synchronization because all 5 federates needed to communicate and stay synchronized during the simulation. Another challenge was managing dynamic ground changes caused by road construction and rover movement. We also had to manage shared resources, especially power and thermal capacity, while maintaining data consistency and integrity. Finally, creating good 3D representation for all 5 federations was another important challenging task. Because of all these challenges, we decided to focus this year on building a strong foundation for our federates, even if we did not implement interaction with other teams We focus on improving and stabilizing our system for the future, and hopefully we would love next year to work with other teams and work more on our fabric. Next slide, please. Also, the next one. Finally, let's talk about what we learned. Through this project, we learned many important things. First of all, it helped us better understand how multiple autonomous systems can cooperate together inside a realistic environment. We gained experience in space simulation, distributed system using HLA and pitch, and learned a lot about resource management, thermal system, and adapting simulation to real-time changes. It was also a great opportunity to improve our technical and teamwork skills by working on a complex simulation project. Next slide, please. On this note, thank you very much for your attention, and we will be happy to answer your questions.
Thank you very much. Next, we will have the National Technical University of Athens.
Good afternoon, Paige. Good afternoon to all. It's a great pleasure presenting at the SE 2026 final event. Many thanks to the coordinating team of NASA and to all participating teams. I'm Panagiotis Michael. I'm a faculty member at the American College of Greece. Many thanks to our colleagues attending the event online. The American College of Greece is an observer this year, with the participation hopefully this coming year. And in today's presentation, I will present and represent the ongoing research work with the National Technical University of Athens. Can change, go to the next slide. Our work builds on the work we have published at the Winter Simulation Conference 2025, where we had also the opportunity to meet physically with colleagues from fellow teams and coordinators from Lunar University and the NASA team. It's a great meeting you all again, even virtually. Our work addresses two subjects. We can move to the next slide. But there's two subjects, the first being the concept of a cardiac center habitat on the moon. Electrocardiogram signals are transmitted through Internet of Space devices to a cardiac intensive care unit. And the second subject addresses the problem of having millions of such Internet of Space, Internet of Things devices that need to be simulated and processed. We're going to address this second problem with the data stream ring architecture we have proposed during the WC 2025 conference. The following slides will present the overall concept and technology. Our work is based on research initiated on the Hoffman cluster at UCLA. You can see the specifications on the table on the right, where we are able to mention that we are continuing our research at the National Supercomputer Infrastructure of Greece, ARIS, where we have simulated 400 million Internet of Things and having response time latency on the order of milliseconds, on average 5. The data rates are approximately 8 million records per second. Our plans, as we see in this diagram, within the context of SE, is to create an HLA interface linking the high bandwidth ring architecture with the pitch runtime infrastructure. This will enable the selective participation to the federation of Internet of Space devices. As an example, among the population of astronauts, Internet of Space devices on the moon, we'll be able to select the ones who demonstrate cardiac problems and allow their interaction with support federates such as the cardiac intensive care unit federate and the ambulance rover federate, and simulating first aid operations. More specifically, we are interested to see the scalability of the solution. Of course, we are not able to connect the supercomputer with pitch due to security purposes for the infrastructure, but we'll be able to run a module locally, capable to scale up to a few millions Internet of Space devices. We'll apply selection of participating Internet of Space devices from approximately a few million Internet of Space devices by using our own stream SQL. And we measure the limits of the experiments in terms of scale, bandwidth, and latency. Can move to the next slide. We have been inspired by lunar operations, and especially from the presentation of Playing Nice Across Time and Space of Mr. Mike Conroy, where he introduces sustainable space-based living quarters, workspace, and laboratories for next generation human spacecraft operations. And our novel conceptual framework suggests, by using the habitat demonstration units, suggests the real-time services in situ on the Moon surface, extending the mature concept of the Internet of Things, introducing the concept of the Internet of Space. And we'll start, as we have already mentioned, with health services. I'll move to the next slide. In this slide, we see the modular approach for the habitat demonstration units, where we have, based on the architecture of the Frankfurt Terminal 3, which has opened in April this year. Based on Terminal 3 architecture, we have developed a modular architecture for the habitat demonstration units on the Moon, which we have named Lunar Port. It's an airport-like infrastructure which can host both the cardiac intensive care unit and also the high-performance computing infrastructure. Move to the next slide. And again, the next slide, these are concepts that I've already explained. Here we see a space data center habitat for high-performance digital stream processing in one of the habitat demonstration units of the Lunar Port. And go to the next slide. And here we can see a cardiac center habitat with a cardiac intensive care unit, again hosted by a habitat demonstration unit in the Lunar Port. Electrocardiogram signals are transmitted through the Internet of Space to a cardiac intensive care unit, and doctor teams, supported by real-time analysis of ECGs generated by state-of-the-art artificial intelligence algorithms, can monitor and diagnose cardiac issues and proactively guide operations teams to rescue humans at risk. Can move to the next slide. This is again our architecture, our data stream ring architecture explained earlier. We can move to the next slide. And some characteristics of the architecture, which was initial work has been, the previous work actually, the Blue Danube work has been published in LS, hosted by IMT Minds in LS conference, the DSRT 2022, and many regards to our colleagues in IMT Minds. We can move to the next slide. The characteristics of the Tariq architecture, which shows a throughput of 5 gigabit per second. And in the next slide, we can switch to the next slide. We can see the low latency of 4 milliseconds on average in terms of performance. Of real-time responsiveness. We can move to the next slide. This concludes our presentation. Many thanks to all, and best of success to SE 2026.
All right, thank you very much. Next we have the Notre Dame University from Lebanon.
Hello, can you hear me?
Yes.
Alright, let's get started. Hello everyone, I hope you're having a great day. My name is Adib Bouzeki. I'm a student at Notre Dame University in Lebanon, and I'll be presenting about our orbital docking system with my teammates. This project focuses on simulating two spacecrafts and the docking between them while using real-time communication and mission control system. Next slide, please. Before we start, I'd like to meet our team. My academic supervisor, Brigitte Assis, and the team leader, Marianne Assis. And this is me and Kirsty Khalifi as the developer team with our teammate, Tara Chaperon, for 3D modeling and simulation development. Next slide. All right, in this presentation, we will briefly explain the components of simulation, the docking scenario, how the simulation was executed and visualized, the challenges we faced, the lessons we learned, and why this simulation matters. Next slide. All right, so our first component or fabric is the chaser spacecraft. It is responsible for approaching and docking with the target vehicle by adjusting its movement and alignment to safely dock, transfer its cargo, and move away safely. Next slide. All right, and this is our second component. This is the target vehicle. And this spacecraft remains stable and acts as the docking destination for the chaser. It confirms the proper alignment needed and receives the cargo once docking is successful. Next slide. And this is our third and final component. It's the brain of the project or the simulation. It's the command and mission control, and it monitors all the mission conditions, decides whether the docking process should continue, pause, or abort in order to maintain the mission safety. Next slide, please. And now I'd like to hand it over to my teammate, Tala.
Thank you, Adib. Hello, everyone. I'm Tala, and I'm going to go over the docking scenario in our simulation. To begin with, it's important to note that all of our federates communicate through the RTI using a publish and subscribe mechanism. The chaser publishes its position, velocity, orientation, and docking status, and the target publishes its position, orientation, and docking port status. On the other hand, the command supervision subscribes to both of these state updates. It receives the data through the RTI, analyzes the relative distance, alignment, velocity, and docking readiness, then decides what should happen next. After that, the supervision publishes commands back to the RTI. These commands are subscribed to by the chaser and includes actions such as approach, hold, dock, retreat, or abort. So basically, the full communication cycle is state data is published by the chaser and target, distributed through the RTI, analyzed by the command supervision, and then commands are published back to guide the docking process. This is really important because it separates the simulation into independent parts while still allowing them to coordinate through a structured communication system. Next slide, please. Thank you. And I'm very glad to say that all three of our federates were successfully visualized. First off, the chaser and the target as 3D models inspired by SpaceX Dragon and Gateway Halo, and the command mission supervision as the dashboard where every parameter and command is being monitored. After defining the communication flow for our simulation, we visualized the docking process in Unity. The simulation shows a real-time docking scenario where the chaser approaches the target while the system monitors important parameters such as relative distance, alignment, accuracy, and docking state. So we also used a multi-camera setup to make the process easier to understand. One camera shows the full approach, another focuses on the chaser movement, and another focuses on the docking port for the precision part of the docking. On the left, we can see the dashboard that we have. This is important because it turns the simulation from just a visual animation into something measurable. It displays the mission values like distance we have, the state, the docking progress, as well as the commands that we can give for our chaser. And we can actually see it visualized in Unity later on. Next slide, please. Thank you. And for the challenges that we faced, we obviously faced both technical and team-related challenges. For the technical part, we mainly faced an issue with the docking alignment. It was not enough for the chaser to simply move toward the target. We needed to have the approach on a correct docking point, align properly, and stop at the right position. Another challenge was integrating Unity with the simulation backend. We had to connect the visual side of the simulation with the HLA style logic. including federates, RTI, communication, publishing state data, and subscribing to commands. That was kind of a big issue, but fixing it gave a very good insight on how different systems and platforms communicate and connect. We also face some blocked content, unfortunately, due to the region restrictions. We live in Lebanon, which made access to certain references or resources very difficult. On the team side, coordinating was challenging among the team members. We are all senior students, so we had a lot of projects on our hands, and we also were working through the war in Lebanon, so we all lost our routines, our stability and peace, and it was kind of hard to work on the project, but we are very proud to be the first Lebanese team to participate in this event and complete the simulation. So that's it. Next slide, please. I'll hand over the lessons learned for my colleague, Christy. Thank you.
Thank you, Tala. This is Christy. Okay, so this slide shows the main lessons we learned from this project. First, we learned that docking is not only about two space staff connecting. It needs good timing, clear signals, and strong coordination between the systems. The chaser, the target, and mission control all have to work together. They need to share the right information at the right time. We also understood space docking better. It must be very precise because even a small mistake in distance or direction can affect the whole mission. And finally, this project improved our teamwork and communication. So overall, we learned how coding, simulation, teamwork, and mission control logic all connect together in one system. Next slide, please. Now, why our simulation matters? Docking is important in space missions. It helps spacecraft connect in orbit. As you can see on the slide, docking is used for crew transfer, cargo delivery, and mission continuation. This helps make docking safer for future space missions. Last slide, please. We hope you enjoyed our presentation, and thank you so much for listening.
All right, thank you very much. The next team is the UCF rover team.
Hi everyone, we're the UCF rover team, and this was our project. Some introductions for the team. Next slide, please. So I'm Bruno Fergosa as a project manager. We have Tanaya McField as a developer, Juan Lorraine as a developer, Ryan as a developer, James Barnett as a developer, and Richard Zhang as well. Next slide, please. So for our solutions, we decided to make 3 different rovers. The Photo Space Institute has a rover on site that they want to see live in simulation, kind of carry out various different tasks. So we came up with 3 solutions. The first one is the Exploration Rover, which is going to be a rover system capable of autonomously navigating an indicated grid of cells, communicating with a map header over the RTI to kind of publish its exploration progress and report back what it has found. Next slide, please. Our second rover is the Mining Rover, which is a rover that gravitates towards identified mining resource deposits. Again, this is the Federate that's going to publish its location, its stock, as well as how much the extraction rate actually is. And for our simulation, there's going to be 3 craters that our rover is going to actually traverse to and begin to mine. Next slide, please. The third solution we came up with is the Construction Rover. So a big goal of ours that Mike wanted to see was to see the tile he had in office kind of be built out in the simulation. So we wanted to make a rover that can kind of carry these tiles and make roads with them. The main goal here being that we aren't exactly sure how traversable the actual lunar surface is going to be in the future. So if we're able to build roads, it's going to be a huge help for the actual infrastructure side of things. So our third rover is going to actually be able to construct a road in a straight line, and it's going to help improve the current infrastructure. Next slide, please. So here's our subsystem loop for the exploration system. So when it initializes, it's going to read its current position and map state, and it's going to determine the next grid to explore. Once that rover picks up the next grid, it's going to move and update the grid accordingly. It's going to send the actual map update with the new grid, and it's going to transmit current progress of the actual grid. It's going to check the percentage of completion, and once it's complete, it's going to finish the actual thing. If not, it'll continue the loop. Next slide, please. Next is the mining subsystem loop. So the rover is going to initialize in the idle state, and our regular deposit is going to initialize, and it's going to publish its position, density, and its depletion state. The idle is going to be listening for that position. Once it picks it up, it's going to move to the traversing state, and it's going to snap at the actual position once it's within 10 to 20 units of the actual regolith crater. Once it's there, it's going to calculate the extraction rate and begin the mining event. And once it has determined that the actual crater is out of regolith, it's going to fire a depletion interaction, which is going to deplete the actual crater. Next slide, please. The last subsystem we made is the construction subsystem. So our rover initializes idle, it's going to traverse, and it's going to begin its actual terrain smoothing process. So we have two states for this, macro grading and fine grading. Once the coefficient goes below a threshold, you're going to begin the alignment state, which is going to trigger our other federate, the tile manager, which starts in the idle state. From here, it's going to traverse between our enums of not holding a tile, holding a tile, placing a tile, and then locking in that tile. And it'll fire an interaction, which our actual rover picks up and begins the seeding process, interlocking process, and the completion process. Once the completion process is complete, it's going to actually register a new instance of the tile in our DOM. That's how we're going to actually kind of animate in a way the road actually looks like. Next slide, please. Our graphics and 3D models, we kept it pretty simple for this project. None of us had any experience with Blender at all, and it's a pretty tough program to digest. So came up with that as our crater, our road tile, which is modeled after what the floor spaces do has live in your office, and similarly the rover as well. Next slide, please. For our tech stack communications, obviously we had the weekly meeting with the C folks on Teams, and we also had weekly meetings and stand-ups on Discord with our team. In terms of source control, we use GitHub as our actual remote repository, and we use Kanban to track our actual tasks and stories. For the federal development, we use Java as our actual language with the C starter kit. We use Blender to actually model them. We use Pitch OMT to work on the actual fonts. And we use the RTI to actually set up a local testing environment. Next slide, please. So for our successes, I would say 3D modeling was one. Like I said, we didn't have any experience, so we all had to kind of just try our best to get something up. We were also pretty successful with the RTI. We know Pitch had a couple of version changes here and there that introduced new things, but we were able to keep the connection pretty steady. The Java class development, so I actually developed the code, enums for all the rover states, the manager states. We all followed standard practices with OOP, inheritance, all of that, so it made it very easy to understand each other's code. Similarly, the team communication was pretty good. We didn't use any extensive Git branching strategies, so we had to communicate what files, who was working on what, to make sure we avoided any sort of conflict. I would also say we were pretty successful with actually architecting our systems. So HLA itself was a pretty foreign framework to all of us, so while we adjusted to the actual learning curve, I would say being able to outline what we actually wanted to accomplish gave us a way to move forward while we adjusted to that. In terms of difficulties, we would say the government shutdown and some other delays kind of got us to a late start. We didn't really start until January, so that was definitely something that we found difficult. Pitch technology was required, and that it also kind of caused a delay in getting our initial licenses. Setting up a reproducible dev environment, we didn't have the server up running at the beginning of the semester, so we had to kind of do everything locally. There's no Docker images for an RTI, and the hardware locks on the RTI make it hard to kind of work outside your main workstation. Developing space font compliant definitions is also another difficulty for us. Kind of similarly to what I was saying, HLA was a learning curve for us, so we kind of tried writing those forms manually. It wasn't until the actual C Discord we saw like there's a kind of GUI you can use to kind of make these forms. That made it a lot easier to actually verify the connection. And we would say legacy code lack of documentation. So while we were actually trying to study what other teams have done in the past, we saw varying structure in the repository as well as a lack of general like readmes in the repos. So it made it hard to actually learn from past teams. And I think that's the end of our presentation.
Infrastructure team who's here in the room with us today.
Hello. Hello, we are the UCF infrastructure team, also known as the UCF base architecture team. I'm Connor Click. I served as the project manager. I also handled server management and some debugging. One of my team members, Alan, unfortunately couldn't make it. He was a Federate developer.
My name is Cody Taylor. I worked on the VPN integration with the website that was involved with that, and I worked on integrating the federates into Dawn, our visualization software.
Hello, I'm Evan Graff, and I worked on federate development, specifically on the Power Systems Federate for this project.
I'm Justin Harper, and I worked on the Logistics Federate.
And we participated in SEE as part of our computer science capstone project. Our sponsor was Mike Conroy with the Florida Space Institute, and our professors were Matthew Gerber and Edward Amarisa. Next slide, please. So one of the core responsibilities of the infrastructure team is getting a set of core applications hosted on a centralized server in order to ensure that the rest of the federates within the simulation can run and get important information. So this requires multiple different local contributor instances running individual federates to connect up to this central cloud-based server, which we do through the WireGuard VPN application. Next slide, please. Drilling down into the actual server architecture, you can see over on the left, we have our core federates. And those are connected up to our RTI on the central server. They're creating the federation execution and joining it and publishing that essential information. Then over on the right, we have our contributors' local federate. They have their own instance of their federate, which is then connecting through WireGuard and also joining the federation execution. Then the information from the RTI gets sent to the Pitch Web Viewer application, which then hosts a web page where that information will be viewed. In addition, the HLA to Dawn federate is also publishing telemetry data to a port, which can then be read by the client-side Dawn application to visualize the simulation. Next slide, please.
So in order to get the client federates connected to the main simulation, the master federate, running on our AWS server, we've used the WireGuard VPN to get all the configurations from both the server and all the clients right for the VPN to connect to each other. We have had to share public keys with each other, and that is what this website is for. So I developed this website for our project where other teams would be able to put in their team name and their public key, submitting it into the website. It then returned config information for them to put into their VPN, automatically configured from the website. And then on the other side of the website, we had a admin dashboard where the admins, that being us or the rest of the SEE team, would be able to look at their public keys and then insert them directly into the configuration for the server. So that way, it was as seamless as possible to get all the VPNs configured and connected to each other. With the admin site, we do have it is protected with a login, and then they also have the ability to edit and delete inserted keys and add other keys that may have not been inserted by the teams. Next slide, please.
So this is the second year that the core federates are being hosted on a centralized cloud-based server. So this meant that this is the first year where a handover has occurred, and we encountered some difficulties from that process being the first time around. One of those difficulties was getting access to the server itself. We needed a member of the previous team to actually insert a public key pair into the SSH authorized keys folder on the instance. Unfortunately, a team member we were in contact with did not have access to the previous VPN server, so we had to build our own, as my teammate just went through. Another one of our issues was version incompatibility. The previous year used Pitch PRTI 5, which is not compatible with the current version of Pitch PRTI, which we are using, which is Pitch PRTI 6. One of the other issues we faced was disk space exhaustion. One of the core applications would basically write to the disk space on the server every time it was started up, and it wouldn't clear that upon shutdown. So that ended up filling up the disk space and was an issue we needed to tackle. And then finally, we had some issues with the HLA to Dawn core federate, in which, depending on the order that it was started up, it could start up improperly and not publish telemetry data appropriately. Next slide, please. So some of the lessons and future improvements that we've taken away from this process is, for one thing, we are compiling, and also we're going to provide the documentation to the next team which will include important information and warnings about the lessons that we've learned and potential things that could go wrong, so that hopefully the process is easier for them. Additionally, it will contain contact information, so that if they do have any issues, they can get in contact with us, and we can make that handover process much easier.
For some future improvements for the VPN site, we've thought about making it so that it is more simple on both our end and the user's end, where whenever they submit the VPN information, on the back end, it would automatically configure it in the server so that we wouldn't have to go into the admin backend, take the VPN keys, and put it into the server. And then we've also thought about making it possible to look up your own configuration that you've already submitted, because currently once you get the configuration, you have to download it or copy it, and then after you close it, it will not appear again for you. So then if you did lose it, you have to go to one of the admins and ask for it. Next slide, please.
So now for our Power Systems Federate, which is the first of our 2 federates we are contributing to this simulation. This is the baseball card for our Power Systems Federate. The Power Systems Federate is essentially going to generate and distribute electricity for the lunar base. It does this by simulating 4 independent control cycles, 1 for a nuclear fission reactor, 1 for a solar panel array, 1 for a battery, and 1 for a power output bus. The nuclear fission reactor is going to generate baseline power for the base, which will be supplemented by the solar panel array. Any excess power will be stored in the battery, and then it will be distributed throughout the base by the power output bus. It's going to execute this power distribution through power requests it will take in from external federates at each time step. It will then sort them by their priority level and then allocate each of them according to the amount of power they requested in kilowatts. Next slide, please. So on the left here, you can see our beautiful 3D model for the power system itself, developed by Cody. And then on the right, you're going to see a diagram of the flow of information in an arbitrary time step of the simulation. So first, it's going to subscribe to data from external federates that it will take in. This data is going to be caught by subscription interaction listener classes, which will then use this information to update the federate state field values that live in the Power Systems Federate class. This information will then be pushed to the update function call, which houses the 4 control cycles of the reactor, the solar panel array, the battery, and the bus. These will each perform some calculations using these values before packaging any necessary information into the needed publication interaction classes, and then publishing this information to the rest of the simulation. Next slide, please.
This is the baseball card for the logistics system. This system serves as the base's inventory and its resource management. This system has control over giving astronauts orders where they will transport resources between different buildings and different federates that other teams have developed. Next slide, please. You can see our 3D model for the logistics on the left there. It's many silos that have ramps where they can export resources, and then those resources can be brought to the rover or other buildings in the federate. And then on the right, we have a diagram of how the logistics system works. You can see 3 example federates, the farm, the mine, and the spaceport that will then deliver items into the warehouse of the logistics system, where then they can be brought out and used throughout the base for various systems.
Next slide, please.
So we have established a couple interactions with other SEE teams federates in the simulation, specifically the Brunel team from London and the Fastens team from Brazil. The Brunel team has implemented a spaceport federate, and the Fastens team have implemented a rover federate. So for our interactions with our power systems and the Brunel's spaceport federate, essentially at each time step, the spaceport will just be requesting and receiving power from the power systems. However, for the rover, the power systems is going to be publishing a rover charging pad object. The rover will have to subscribe to the location of. It will then have to navigate over to the charging pad before it is able to request and receive power. Finally, for our interaction between our power systems and our logistics systems, the logistics systems will be requesting and receiving power from the power systems at each time step as well. However, the power systems will also be requesting and receiving fuel from the logistics systems to generate this power.
So for our interactions between the rover federate and the logistics federate, so the spaceport federate will first have a lander land. Sorry. The spaceport federate will have a lander come in and land. It will have resources on hand, and then we'll send out a request to the logistics federate and have those resources picked up. Additionally, we'll send out a request to the rover federate. The rover federate will then go to the spaceport, pick up those resources, and then transfer them over to the logistics federate. Then, upon receiving a notification that the lander has run out of fuel or needs refueling, it will send out another request over to the logistics federate, which will then call over a rover federate to bring the fuel from the logistics system over to the rover, or over to the spaceport. And that is the end of our presentation.
All right, thank you guys. All right, last for the student presentations, we have the UCF Young team who are also here with us today.
Hello, we are the Distributed Observer Network team. You may have seen us mention some of the other projects. My name is Andrew Sperry.
My name is Golden. And we have some here joining us through Teams. So,
yep, my name is Lunar.
For some context around Dawn, the next slide please. For some context around Dawn is a space simulation software for visualizing and replaying spacecraft missions. And to use this, you would upload 3D models along with telemetry data, which describes how these 3D models move over time, and then a recording would then be generated, which can be viewed inside Dawn. Next slide, please. We worked on a few MVPs, and what motivated these MVPs is that we want to make Dawn more usable by, more easily usable by users, as well as make Dawn much more easy to work on software for future teams, and also make Dawn a little bit more collaborative. Next slide, please. Oh, sorry. So our 3 MVPs, if we go back one slide, is blueprint refactoring, building it to an executable, and then implementing multiplayer functionality. Next slide.
So the first MVP is converting blueprints to C++. So currently Dawn is running through the Unreal Engine, and the Unreal Engine uses something called blueprints. It's more of a visual way to code. It has a lot of blocks that stores information. However, this project's been worked on for about 10 semesters now, so it's grown very large. These blueprints are massive now. They're very hard to scale. It's very hard to keep working on because they are just super lengthy and become difficult to read. So we wanted to convert them to C++ because we give bigger long-term flexibility. And also, a lot of the blueprints just end up being duplicated throughout the years and just get very complex. So you can see here, those are what some of the blueprints looks like. We just ended up completely removing them. We have a ton more examples like this, but these are just the ones that we showed off. This one manages the camera speed, so it's just been completely converted into a C++ function as opposed to all of this.
Alright, so for our second MVP, this was the one that I worked on, was building Dawn into an executable file. So originally, the only way to run Dawn was to go into the Unreal Engine, download it, get all the plugins, and then go through the sensor documentation to set up the project, which is a very long and tedious process. And Unreal Engine itself is a very GPU heavy, RAM heavy software. So building an executable, it allows it to be opened by anybody with even less requirements for a good type of computer. Originally we weren't able to open it on our laptops, the Unreal Engine itself, but now we can have it work on our laptops. And it's a lot easier to share around. You just put it in a zip folder and you can send it to anybody. So if we go to the next slide, this is just showing that the size difference. So before, those were all the files you needed to open up Dawn and mess around with it. It took up about 70 something gigabytes. And now the new one, there's a lot less folders, a lot less files, condensed it all, and now it only takes about 2 gigabytes. And even in the executable itself, Dawn runs way faster than it ever could with an engine. So with this, now Dawn can be shared around, the newest version can be shared around very easily, and it works a lot faster and a lot better. Next slide.
Our final MVP is multiplayer. So we want to make Dawn a lot more collaborative, interactive with other people. So we implemented a multiplayer feature where users would be able to join a simulation with each other and explore the simulation together or point to certain events inside the simulation. Next slide. And so we implemented some features. The first feature here is visibility, so you would be able to see all the other users inside the simulation, see what they're looking at, see where they're going towards, or maybe the way they're rotating in the direction they're looking at in the simulation. Next slide. We also implemented player teleportation, so you'll be able to instantly jump to another user's location inside the simulation. Next slide.
The next thing we did was add to the media controller. So originally, if the simulation plays, both the hosts and the clients can edit what time step it's on, and this causes the simulation to get extremely out of sync very quickly. So we made it so that only the host has the ability to change what time the simulation it is, and the clients can just see the exact time step and then what speed it currently is at. Next slide. Next thing we decided to add was player pings. So now both hosts and clients, they can press Q, and then this beam light will be dropped from the sky. This will be visible from extremely far away, so it allows for more player interaction, and if someone wants to show something very specific happening on the simulation, everyone will be able to see what they're looking at and go to that point. Final thing that we did was add proper cleanup to the simulation. So this would be a good file if it's loading properly, but what would happen is if the host would leave while there's still clients in the simulation, those clients would be completely trapped and it would completely restart the project. So what we did was we fixed it so that they would get a warning and a pop-up that they're going to be kicked from the game anytime a host leaves for 5 seconds. After those 5 seconds, they'd be brought back to the main menu. Then our final slide, it's just like, if it's okay, just show like the last minute of the demo. You might just want, I don't know if it'll work, if not, it's fine. And then you might just want to mute it and I'll just talk over it. And then you can just run to like the very last minute. That's fine. A little bit further, probably like 5:30ish. So yeah, this is our join game, load game. But yeah, once you're in the simulation, you can see there's now another person there. And then those are also the bottom. So in a second here, you see that we can drop the things on the ground and it'll be visible. I'm currently a client. You can see I don't have like a timeline running. So then if you go like just a little bit further, you'll just see how the simulation runs. It's like 6:20. Yeah, that's good. So this is the spacecraft. It's going from Moon to Earth, so you can see it also the clouds inside Earth. And then now we're flying back to Mars, and then you can still just see how both of the ducks that are both of us are still visible. That's what I was trying to show off real quick. And yeah, that's when we lose the session early, and just get kicked back to the game. So that's about it.
All right, thank you very much. All right, so that concludes the presentation portion of the final event. Now, you may have been wondering for the last hour and a half why we have a bunch of people up here with laptops. They did present for a bit, but we also are going to be navigating to the Federation execution portion of this event. So we saw several teams design their own simulations, or federates, that's the distributed simulation word for simulation is federate. Several teams designed their own simulations, built simulations, but a few of our teams completed them and actually integrated them into the full distributed simulation. So up here we have our infrastructure team, as you saw their presentation. So they were in charge of the server. So I'm going to have Connor go ahead and share his screen. Make this bigger. So the infrastructure team was in charge of our AWS server, as you just heard. So you are taking a look right now at the central server that's hosting our simulation execution, or federation execution, as we like to call it. We have those 3 core federates that they talked about. So we have the Space Master. So this one controls the execution control, and it also controls the timing, which we call our pacer. We also have the Space Reference Frame Publisher. So those of you familiar with reference frames, it orients you in position and rotation in space. And we also have HLA to Dawn. So you just heard the Dawn team talk. This is our visualization tool. It listens to all, this federate here listens to all the simulations currently running. It pulls out the state data, and that's what lets us view it in a graphics engine, Dawn. So these are the core federates. So once they join the simulation, it is effectively running. So time is currently advancing. This is a live simulation happening right now, being controlled here by these guys. So we're also now going to kick it off to a few of our universities that have simulations to join. So first, we're going to go ahead with Brunel.
Hi, Paige. We're going to get started by launching the Spaceport Federate. And looks like it's joined the Federation. We're going to go ahead and launch the Lander Federate next. All right, looks like it's joined the Federation as well. Both Federates seem to be functioning in time. Thank you.
All right, thank you very much. Bassins, would you like to join your simulations?
Hi Paige, can you hear me?
Yes.
I'm joining the rover Federate. Wait a second. Some exceptional period, but it's not the same the last day. So I will try to run it again. Okay, now it starts running. Okay, rover Federate is launched.
Perfect, thank you very much.
Thank you.
All right, UCF, infrastructure team, would you like to join?
All right, I'm going to join the Power Systems Federate now.
And just to narrate a little bit, you can see as each team is joining their simulation, you can see another bubble appear. So this is each of the simulations represented as one single bubble. We call this our lollipop diagram.
I'm now running the logistics system federate. And that is all of our federates.
All right, thank you. UCF rover team, would you like to join your federates?
Yep, I'll be joining the regular federate first. Alright, should be connected. I'll be launching the mining rover next. Next, I'll be launching the exploration map federate. The exploration rover itself. And we have the construction rover. And lastly, the tile manager federate. The UCF rover team has finished joining their federates.
All right, thank you. IMT Mines, would you like to join your federates?
Hey Paige, yes, so we're going to launch the waste storage system. And it should be up, yep. Now we're going to launch the waste disposal system, dismantling system, sorry. And it's running. And lastly, we're going to launch the waste transformation system. And it's connected. We have launched all of our federates.
All right, thank you. And NDU, would you like to join your federates?
Sure thing. Hi, Paige. I'm going to start in with the Chaser Federate. Perfect, seems to be connected. And then with the Target Federate. Cool, that's on. And finally with the Command Mission Supervision. Perfect, all is up. Thank you, Paige.
Excellent, thank thank you very much. And with that, we have joined all of our team federates. I want to say a big congratulations to these teams. This is a huge accomplishment. It's very All right, now we're going to give a chance for each of these teams to show you what exactly their federates are doing, because right now all you know is that they've joined, which is already incredibly amazing. But we're going to give them a chance to show what's going on behind the scenes. So our first teams, we have a few teams that are doing interactions together. That means their simulations are directly talking with each other, and they work together on this to make this happen across time zones, across the world. So these teams will be Brunel team from London, the Fastens team from Brazil, UCF infrastructure team from Orlando, and the UCF rover team also from Orlando. So go ahead and take it away, guys.
All right, and then let me just find. That's fine. So here we have the dawn visualization. Let me just get in view. Here we have the dawn visualization. This is real time, so as you can see, the Brunel team's lander is now taking off, and it will come back down with a cargo delivery. Here, Danshu, do you want to give an explanation, a more in detail explanation on what the lander is doing?
Sure, Connor, thanks. So the combined simulation scenario that ties our simulation with Fastens and UCF begins with, as you're seeing on screen, a lunar lander that is on its final approach to the lunar surface. And so the lander sends out a landing request to any spaceport that's available to grant clearance. So once a spaceport accepts it, the lander proceeds to land there. So once it touches down onto the spaceport platform, that's when the spaceport will dispatch an interaction to the Fastens rover to retrieve cargo from the lander that just arrived. And from that point on, the rover will carry the cargo over to the UCF logistics warehouse, and shortly afterwards, the spaceport will send yet another request, this time to the UCF logistics warehouse, asking for cargo to be delivered to it so that it can replenish the lander's resources and prepare it for a return journey. So with the cargo loaded on board, the lander will then take off from the spaceport platform. So while all of this is going on, the spaceport is, of course, continuing to draw a certain amount of power from the UCF power systems federate. And during cargo transfer periods, that's when the power consumption of the spaceport kind of kicks into peak mode, where it consumes the maximum operational capacity to enable cargo transfer via its robotic arms. Although we don't have that graphically rendered here in Dawn, it is happening in the actual simulation model in the HLA. And so this interaction cycle pretty much repeats ad infinitum. Thank you.
All right, and just to show the rover going back to the logistics center, we have a rover here, which is now returning with cargo. So now that the rover is deposited, it will return to go service another spaceport. And that is all of the demonstration of the interactions between our federates. Eventually, the rovers will start to run out of energy, and when they do, they will go to the charging pad to charge. However, that will not happen for a few minutes. All right. Then, Bruno, do you want to start to go into what your federates are doing?
Yeah, so we can start with the construction rover. So if you kind of zoom in a little bit, you might have to move forward in time.
I believe this should be current time.
Yeah, I guess it's not picking up the actual tile objects at the moment. We could look at the mining rover instead then.
All right, there we go. It's just deposited at the crater. 1 second. There we go.
So it's just moving from crater to crater. Once it lands at the newest crater, it's going to stop and actually begin the mine. Looks like the rover's stuck under the terrain, but
Yes, apologies, that's just a later rotation artifact.
Yeah, that's a very difficult problem to solve when you've got a terrain and you're trying to propagate with state, and you've got to get the contact modeling for your vehicle to match up with the terrain, and understood.
but looks like it's at least on its way out in a way, and it's going to the next crater. Once it'll land there, it'll stop, and that's when the actual, if you look at the RTI logs, it's when it's actually mining the crater. And it'll stay there for a little bit, and once the depletion event happens, it'll move on to the next one, if there is a next one. If not, it'll finish there. But that's the mining rover. You can take a look at the exploration one. So this one's going to be in yellow. This one's essentially just going to be traversing in a kind of like a square-like pattern. It's just going row by row. And every second that the timeline actually increases, it's going to send to our logs event a kind of like an ASCII state of the current map. So 0 means it's not been explored, 1 means it's been explored. So if you compare that to what's happening visually right now, you'll kind of be able to like actually keep up with what the progress is. But once that grid that we kind of determine upon initialization is complete, the rover will stop moving. Okay. And the construction rover, see the tiles begin to place. Looks like there's a visual bug there.
Yeah, I think the model for the tiles might not have been put in correctly.
Yeah, that might be it. But essentially, you'd just be saying some tile objects spawning right below the rover. It should be 14 of them. That's how many we put as a limit, because otherwise it'd be infinite. But that's our simulation right now.
All right, then that concludes the interactions between the 4 teams.
Connor, wouldn't it be okay if I just explain a little bit about the functionalities of our rover?
Sure thing.
Okay, so first of all, when the lander lands, it will send a pickup job request to our rover. At this moment, the LLM integrated in the rover feather will read the request and take a decision on which rover should accept the mission, and in case of more than one mission, which mission it should be accepted. This decision is based on the state of the rover, for example, its charge, its current load capacity, and the information about the requested mission at all. So, for example, coordinates of pickup and delivery. In our current case, the rover always moves to the spaceport where the lander landed, picks up the cargo, and moves to the logistics federate, transferring the cargo. The 3 rovers keep the cycle of pickup and delivery among the spaceports, and of course expanding energy. So when the charge of a rover is low, that rover finishes its job and waits for the next LLM decision. The LLM will consider the low charge information and send the rover the command to recharge at the charging pad object at power systems before accepting more missions. It will take a while for the battery on one of the rovers get low. So I think it's basically for our presentation. Thank you everyone very much for listening.
All right, excellent job, guys. We'll next move on to IMT Minds.
Yes, I'll share my screen. Can you see it?
Yes.
Alright, so we've basically captured the video of these 3 federates working. So it starts with basically one of the objects coming in, and it goes through a scanning module that will decide where it needs to go. So the first object would go to the dismantling module. So in this case, it should be dismantled. into its basic components. We didn't fully capture that in the simulation. Hopefully for next year it will be. And then it goes to the storage system where we have basically a crane that will pick it up and then store it in one of the compartments, which is made for basically all the materials and such, so the first one. So in the meantime, we technically had another box coming in, or the presentation of the waste coming in, and then through the scanning system, it basically went and the results were that it could be repaired. So if we were to follow it, it's going to the transformation system. So after some work that's done, it will go back to the storage system. The crane will basically pick it up and then put it in its corresponding place, which is for everything that's been repaired. So later on, it can be picked up for delivery for whatever system calls for it. So that's basically our 3D model systems. Now in the back end, we have additional capability which we didn't include in the basic simulation of the model, but it's basically going interactions between the storage system and the transformation system. So it would be more like requests about for production and such. So yes, this is all from us.
All right, excellent, thank you very much. All right, lastly, we have the Notre Dame University.
Hi, I'm Paige. I'm going to show my screen.
Yes, go ahead.
Right. So on your right, you will see the real-time visualization of the simulation going on Unity, and on your left, you can see my dashboard. Now our chaser will have some supplies needed for our team style mission. You can see all our supplies right here, and as I press approach, you will see my chaser approaching the target. Now during this phase, the chaser is continuously giving updates to the RTI, so we can monitor all the relative distance, and as it's approaching, we can monitor everything. It reaches a point where the relative distance is at the KOS, which is the keep out sphere, basically a safety sphere around the target to make sure that everything is fine. As long as I enter KOS, since it's a critical point, I have to make sure that the retreat test is fine as well. So as I go with the retreat test, I can see that my chaser is going back to a safety plan. And as that is possible, I can resume back to approaching my target at a lower rate right now because it is getting into a critical state as well. So you can see the chaser approaching. Excellent. Now at a certain distance as well, we will enter the final approach stage, which is a slower rate approaching as well of the chaser. It will appear here in our camera that is focused on the target. So we can see it slowing down and slowly reaching the target with perfect alignment. And as you can see, as closer as it gets slower to make sure that everything is safe to dock. Excellent. Now it's confirming the docking. The docking is in sequence. Perfect. now that the docking is done, we are safe to transfer the cargo. So on my dashboard, I can transfer cargo, and we can see it in transit happening in real time to check all the supplies that we have on the chaser. So as that is done, we can track that as well. Excellent. So once every supply is being transferred, we can safely undock now, and we can see it visually on Unity as well, undocking, and obviously fly away from the target. Thank you so much, and I think that's it.
All right, that concludes the Federation execution portion of this event. I want to say again, congratulations to all the teams for making this happen, both the teams that did the presentations as well as the teams that did the Federation execution. This is incredibly advanced technology, so congratulations. Now, the last portion of this will be a little bit shorter than the rest, but we do have a panel of experts that's been listening in. We have people from industry, from government, from defense that have been listening into these presentations and that are going to give some short feedback to our teams. I'm going to first kick it off to Alfredo Garo. If you could please introduce yourself and give some feedback to our teams, please.
Hi, Paige. Good afternoon, everyone. Thank you for moving my short talk earlier in the agenda. Sorry, but I am traveling, and at the moment the Wi-Fi at my hotel does not work properly, so I am connected by using my smartphone as hotspot, and so for maintaining a stable connection, I am going to turn off my camera. I hope that my connection will be stable. I apologize for that. So I would like to give you just a message about the importance of standards, and obviously it's a pleasure for me to speak today at the plenary event of the C project. And when we talk about the future of simulation, especially in the space domain, there is one concept that becomes absolutely fundamental, and this is interoperability. And as you know, modern space missions are no longer developed by a single organization using a single monolithic simulator. Indeed, they are collaborative ecosystems that involves agencies, industries, academia, operators, engineering teams, training systems, digital twins, and increasingly also autonomous systems distributed across the globe. So in this context, the standards are not just technical details, but they are strategic enablers. Distributed simulation standards allow independently developing of systems to communicate, exchange data, synchronize time, and operate coherently inside the common simulation environment. Without standards, every integration becomes a custom integration that can be expensive, fragile, and difficult to scale. With standards, however, we can build reusable ecosystems where models and tools can evolve independently while still working together. So this is particularly critical in the space domain because we must be precise, timing, coordinate systems, dynamics, communication, operational procedure are critical. This is why we worked in developing standards such as the space phone that you use it in your experience. And what makes this especially meaningful is that standards like space phone are not theoretical exercise. They are already being applied in the major programs, including Artemis-related simulation activities, and also supported by contribution from agencies, industry, academia, and so on. So this collaborative approach is essential because a single organization can address alone the complexity of future space ecosystems. And in many ways, standards are the invisible infrastructure of innovation. They allow competition where it matters in ideas, technologies, and capabilities, as you showed us today, while ensuring collaboration where it is essential in communication and interoperability. As simulation becomes increasingly central to engineering, operations, AI integration, digital twins, the importance of open and shared standards will only continue to grow. So projects like CE are therefore extremely valuable for me, for us, because they help build not only technology, but also the culture of collaboration that future space exploration will require. So I would like to thank you very much for this experience, and I hope that you enjoyed this CE edition. Thank you so much.
All right, thank you very much. I'm now going
Thank
to
you,
pass it
Patty.
on to Mike Conroy, who's here with us in the room.
Hello, thank you everybody, thank you for staying, for being here. What you saw was a set of models of sims you saw stuck put together this way. We looked at it, we saw the technologies, we saw how they went together. This is also a part of something bigger. This is also a projection of a bunch of future states of what could be possible futures that are out there that may work. We can go test them in this environment, see how they work together, see how they interoperate. It's pretty much a time machine in the future to really predict, is this a good idea or is this not a good idea? This is the digital engineering aspect of what's here, and this is what brought me to it. When we talk SIM from the NASA side, that's a lot of what we're looking at, right? That's a lot of what we're looking at there, is looking at things that way. Alfredo mentioned digital twins. Digital twins is a part of this, but this is where the digital twin is built first. You look at the twin, and you aren't representing an existing system so you can use it offline. You're representing a future system with your time machine. You go see what's going to go work best and how it's going to go pull all together. I'm comfortable with describing that because, not meaning to, about 15 years ago, a friend Mike Chapto and I wrote part of the NASA Falling Simulation Roadmap, and that's where the digital twin started showing up. It was a nomenclature that was in there, and we get still getting a couple of citations a week on that one. From how the panel fits, we talked about Fredo. This is, what do we think of we've got different elements that we're going to review and that we're going to go look like. From my point, it's the technical implementation, the systems we're going to put together. I took some notes as this went, and all the teams started out trying to understand the intended environment, where they were going, not their digital environment, but the moon. What's the moon look like? How's it going to fit? How's it all put together? That's fantastic. That's how it's supposed to work. Figure out, learn everything you can about where you're going to go be. Figure out how you can do the thing that you need to go do, and then look at what are your friends going to go do, because we're not going to do this alone anyway, and these people found with their friends, found how to go integrate, found how to go share, to get a better look of what that future world is like. That's a very, very powerful way to look at it. Frankly, from my point of view, it's the only way to go look at it, and I think all of the teams did an exceptional job in that area. They partnered, worked out the pieces, and grew complexity. The next time you're talking to somebody, or they're saying, yeah, this whole distributed engineering that chases time zones, they're going to do this, where you work everybody together, and doing it with the real hard math, not just PowerPoint engineering and things like that. They tell you that the high level stuff's not going to work. It does. These kids do it. They did it, no problem. NASA does it as well. We just can't talk about it at all. These kids, I call you kids because I'm an awful lot older than you are. You just have to live with that, sorry. It's been going on for a while. It will continue to go along. These kids here, the kids that were the rest of these systems that were out there, fantastic job pulling this together. This is how you solve big, hard, nasty problems with a bunch of people, with a bunch of friends from a bunch of other locations. The cold stations you just written, so we went through that. I would call that the cleanest and fastest one ever in time by an order of magnitude. So fantastic job to all the teams. For technical implementation, usually you say something like, well, you have a problem here, you have a problem here. That looked pretty much flawless to me. Fantastic. Good job with the infrastructure, teams that were joining. Good job with y'all with all of the things that you did there. Next, I'd like to see if Zach's online. Zach, are you here?
Yes, Zach is here.
And Zach, do you have some thoughts for us on infrastructure and the development and things that you saw here?
Well, I was very impressed with the infrastructure. I think in the early days, because a person named Dan Dexter, who's not on the line here today, couldn't be on with us today, and I started off the very early days of the C program by literally hauling big switches and getting network drops into rooms and setting up tables and putting computers together and setting up RTIs and putting holes through firewalls in order to get everything to be able to communicate, and it was very fragile. And now the advancements of the technologies with the web services and the ability to virtualize machines and set it up with a generalized infrastructure using VPNs, virtual private networks, has made the whole system a lot easier to set up, to use, to operate, and to understand. And so there's been a lot of advances, and I've really enjoyed watching the infrastructure teams learn and put this stuff together and teach us old folks how to do things. So I really have been excited to see where it's going. I really appreciate the observations that the infrastructure team made as far as learning the lessons of what worked before and what didn't work before, and making plans to correct that for the future, because that's how we advance. Basically, if something happens and it goes wrong, and you observe, you see what it is, and you say, okay, that's great. If you don't do anything, then it's just a lesson observed. It's not a lesson learned. It's not a lesson learned until you pass it on to somebody else and they have a chance to fix it. And I think that's what you've done here, and so I was very impressed by how that worked. And I think it's shown us as an organization, C as an organization, some of the things that they can do to improve in the future as well. And so I encourage you to pass that information along, share it with your technical chair and the technical committees associated with C, so that we have an opportunity to make things easier for the next teams that come along. And overall, I thought the way that the teams interacted together on this one was exceptional. It is one of the smoother sets of tests that I think we've ever seen. And I thought there was a lot of great work done by all teams, and I look forward to seeing what you all are going to do in the future, both in the next C events and in your professional careers. Congratulations.
Thank you very much. One thing real quick that Dr. Cruz brought up is the fact that we're running this out of the cloud. A little shy of a decade ago, one of the teams came to us and said, we can run all of this out of the cloud. And the owners from Pitch, or the people from Pitch, the people from Mock, the people from all the architects said, there's no way our stuff will run in the cloud. And so they said, would you like to see the test scripts? So they put it on the table. And from then on, we've always run in the cloud. It was the SEE team that figured out how to go do it, or the UCF SEE teams figured out how to go do that. And about 3 months later, you started seeing Amazon compatible at the bottom of the web screens for the different vendors that were selling all the tools that the students showed them how to go run in the crowd. So there's real positive work that's done by these teams and how they go work through this. Stefan, are you around?
Yes, I am.
Fantastic, sir. Will you talk to us a little bit about Federates and the models and things you saw developed?
Yes, sure. Let me briefly introduce myself. I'm Stefan Straßburger from Lunar, Germany, professor for simulation. I've been around and involved with the HLA, I think since the very beginning. So I've seen a lot of federates and models in the HLA, both in academia and also in industry. And well, enough about me. Let me say, I'm impressed by your models and your federates that I've seen today. So you all did really well. We had surface vehicles, like the different kinds of rovers, cargo rovers, construction rovers, that emergency response vehicle. We had space vehicles, the chaser spacecraft, the target vehicle, I think you called it. I must say I was really impressed by that one from the team from Lebanon. So well, you all did well, but this one, it really stood out to me as a kind of an observer. And then we had the infrastructure models like the Lunar bunker that looked great to me, the waste storage facility, logistics federate, the power stations, the Lunar solar, and the Power Systems Federate. So, well, I must say I'm impressed by your models. So that's all I gotta say. Carry on with that.
I believe our last panelist is Bjorn. Bjorn, are you with us?
I am
Oh,
with
fantastic.
you.
Good to see you, friend.
Can you hear me loud and clear, I hope?
Yes, sir.
I'm sitting here in front of my favorite astronauts behind me. Well, I'm blown away. Like some of you may know me, some don't. I'm one of the founders of Pitch, who provided this software for you that you took to another level by developing some great simulators. I've seen a lot of simulators and federates over time, but this is always the highlight of the year to see this final demo and look at the innovation happening. And there's even more innovation this year. I'm so happy to see, like the Brunel, who interacted with Fessons and UCF, and also I was very interested in the CHLA starter kit too, with the C base plate. I'll take a look at that afterwards and look at the slides. And Ember Riddle taught me a bit about survival conditions, oxygen, temperature with this federate, which is very interesting. And on the innovation side, from our Brazilian friends, using AI and LLM as part of the decision making. That's really cool. I like that. I learned about moonquake mitigation from Florida Poly team, and also IMT Minds had a very interesting interaction matrix. So that's a nice way of documenting how things play together. And along those lines, the Lille Catholic University took the federate synchronization, actually developing 5 federates to the next level. I'm also very interested to see on the future of HLA connected to the ring. It's not the ring of the Lord, but the ring of InfiniBand, I think. And also the UCF rover team. And when it came, I have to agree with Zach that the base architecture team, I'd love to see those kind of architecture teams with many of the customers out there use them. And also Dawn getting a facelift, that's really great. What impressed me more than anything else was the professionalism from NDU team Lebanon. Very nice, professional, clear architecture, visualization, coordination control, and also doing this under the very challenging conditions now in Lebanon. So thank you everyone, fantastic job, thanks.
Thank you very much. Back to you.
All right, thank you very much to our panel of experts. As you saw, we had people from NASA, from universities across the world, industry, so we're really grateful for them to come and give feedback to our amazing teams here. Now, before we wrap up, I would like to invite everyone online to turn on their cameras and everyone in person to come up to the front so we could take a picture of us all together. We are all distributed across the world. We have 3 different continents, 7 countries, so it's really amazing that we get to pull this all together in the end.
Watch on YouTube. Do it on 3. I'll do it twice. Oh, let me pull back. 1, 2, 3 once. 1, 2, 3 twice. Gotcha.
All right, and thank you everyone. With that, C 2026 is officially over. I invite everyone that is eligible to come back next year for C 2027. Thank you everyone for attending.
Well done.
Thank you. Bye.
Thank you. Bye.
Great job, everyone. Bye.
Thank you. Goodbye.
Bye. Good job.